The era of speculative venture capital and flashy 3D rendered flying cars is permanently dead. Right now, tourists in China are taking active flights in electric air taxis. Meanwhile, highly funded pioneers in Europe and the US are facing years of delays, and in some cases, outright bankruptcy. Why is there such a massive disconnect in outcomes between different geographic regions? The winner of the AAM race isn't being decided by who builds the best aircraft. It is being decided by how local regulators balance theoretical safety against industrial pragmatism. To understand this regulatory battle, you have to look at the foundational physical constraint of all electric aviation: energy density. Energy density is the amount of power a battery holds relative to its physical weight. Modern lithium-ion batteries hold significantly less energy than traditional jet fuel. Because of this, every single kilogram of added structural weight severely reduces an aircraft's payload capacity and flight range. Engineers must strike a delicate balance to make a flying taxi capable of lifting passengers. This creates a regulatory trap. If a government demands too many redundant safety systems, the resulting structural weight destroys the aircraft's ability to fly a viable commercial route. A regulator's specific safety philosophy directly dictates whether a flying taxi becomes a multi-billion-dollar business or a physical impossibility. In Europe, the European Union Aviation Safety Agency, or EASA, took a highly prescriptive, uncompromising approach to urban air mobility. EASA is the primary agency responsible for civil aviation safety across the European Union. They chose to apply the massive, nearly impossible mathematical safety thresholds of large commercial airliners to small, short-range electric air taxis. As a result, European startups were forced to build immense, heavy redundancies into their fly-by-wire avionics and battery packs to hit theoretical perfection on their very first iteration. You can see the physical result of this regulatory burden on aircraft like the Lilium jet prototype. The rigid weight penalty imposed by EASA's rules destroyed payload capacities under current battery chemistry. This directly caused severe capital exhaustion and the high-profile insolvency of companies like Lilium. Europe's ideological framework essentially mandated a level of theoretical public safety that completely outstripped the laws of modern battery physics, suffocating its domestic pioneers. Contrast this with China, guided by the Civil Aviation Administration of China, or CAAC. The CAAC is the national aviation authority overseeing all civil flight operations in China. They operate under a top-down, state-mandated directive to quickly build the low-altitude economy. Instead of demanding perfect mathematical simulations up front, the CAAC builds its safety case through empirical, trial-and-error physical testing. The regulator grants significant weight exemptions of up to 5,700 kilograms, allowing manufacturers to use heavier, robust battery packs without failing certification. This pragmatic flexibility allowed specific hardware, like the EHang EH216S multi-rotor aircraft, to successfully navigate the system and achieve full certification. By allowing over 40,000 test flights and utilizing the massive pre-existing drone supply chains in Guangdong province, China has reached active, revenue-generating commercial operations years ahead of the West. China is winning the race for immediate deployment by pragmatically treating early air taxis like advanced geofenced drones rather than complex airliners. The United States is taking a different path, with regulators attempting to balance European safety rigor with industrial innovation. The bureaucratic authority managing this balance is the Federal Aviation Administration, or FAA. The FAA is the primary federal agency responsible for regulating all aspects of civil aviation in the United States. The FAA uses a performance-based standard. They evaluate these small air taxis with a risk model closer to traditional light helicopters, deliberately avoiding Europe's commercial airliner tap. This flexibility allows U.S. companies to pursue a deeply complex engineering challenge known as transition flight. Transition flight is the phase where an aircraft shifts mid-air from vertical rotor lift to horizontal aerodynamic wing lift. You can see American aircraft actively executing this unforgiving aerodynamic maneuver in flight tests today. Mastering winged transition flight yields significantly higher speeds and longer intercity ranges compared to the short-range multirotors dominating early Chinese operations. A unique domestic synergy makes this possible. California venture capital funds the complex software, while Ohio provides the uncongested military airspace to relentlessly test it. The U.S. is actively sacrificing immediate, localized launch speed in order to engineer deeply complex, highly scalable vehicles capable of integrating safely into legacy global airspace. While U.S. manufacturers are building highly capable aircraft, they still face years of methodical, for-credit safety testing and local zoning friction at home. That makes the United Arab Emirates the ultimate commercial accelerator, a market specifically designed to bypass Western infrastructure delays. We are already seeing the physical integration of U.S. hardware into the Middle Eastern infrastructure vision. The UAE is aggressively harmonizing its rules with the FAA and deploying massive sovereign wealth to create monopolistic, ready-to-fly environments for U.S. companies by 2026. The Middle East has positioned itself as the indispensable revenue-generating proving ground required to validate American technology for the broader global institutional market. This chart maps the global industry landscape based on the two most critical metrics defining success in 2026. Speed to market on the y-axis, and engineering scalability on the x-axis. Looking at the data, China plots very high on speed due to their regulatory velocity, but lower on global scalability. Meanwhile, Europe plots at the absolute bottom for speed, effectively trapped by its own rigid safety weight constraints. The United States plots securely in the middle for speed, but sits at the extreme far right for maximum scalability, thanks to its complex transition flight goals. If an investor requires immediate, state-subsidized commercial proof of concept, the Asian market is the undisputed reality today. But for those betting on long-term technological moats and the establishment of global aviation standards, the U.S. regulatory and engineering ecosystem holds the definitive advantage. The hype cycle is now permanently over. The survivors of this multi-billion-dollar race will be the companies that successfully turn rigid regulatory boardrooms into active operational runways.